Okay, this is problem 5.26 from the back of the textbook. The problem tells us about a sample of sulfur hexafluoride gas SF6. We'll see this later when we study the VSEPR model, because it's got an octahedral geometry around the central sulfur, so it's a nice example of that. But anyway, it's a nonpolar molecule, so it's a gas, even though it's sort of heavy for a gas in terms of molecular weight. We initially hold that at a volume of 9.1 liters at a temperature of 198 degrees Celsius. Then we take that same sample, we do not change the number of moles, we keep the number of moles constant. The same sample is then cooled while maintaining a constant pressure. So pressure is constant, number of moles is constant, until the final volume is 2.5 liters. So the only reason the volume is shrinking is because it's initially 9.1, it ended up at 2.5. It's a shrinking volume, right? The only reason why it's shrinking is because we're cooling the gas down, causing the gas molecules to move slower, and at constant pressure that causes a decrease in volume. Now, if all that's true then, what is the temperature in degrees Celsius that's required to cause this reduction in volume? Okay. Now, as I look at this, again, I always start a gas law problem by taking account of what information that I've got. Okay. Well, first off, there's usually two conditions, kind of like a before and an after, right? It's pretty common in these types of problems, so you can almost write before and after. Before, the initial volume was 9.1 liters, and the final volume was only 2.5 liters. Okay. We know the pressure is the same, we know the number of moles is the same. Well, what else is changing? The temperature, right? Before, at the initial, the temperature was 198 degrees Celsius. At the final temperature, we don't know how many degrees Celsius it is. We're trying to find that actually, okay? But we know there's some temperature that makes this math all work out, okay? And that's, of course, the trick, is we have to find that temperature. So clearly then, if we look at this, the way this is set up, this problem, from an instructional point of view, is aiming to examine this Charles law constant, Charles law concept, which is the relationship between the volume and the temperature of a gas. And basically what this law tells us, in contrast with Boyle's law, the Charles law relationship tells us at constant pressure and number of moles of gas, that my volume divided by my temperature is K, a constant, okay? So the way that I functionally usually use this in like comparing before and after then, is since it doesn't matter what temperature I'm at, what volume I'm at, okay? As long as the pressure and the number of moles is the same, I can have two conditions, a before and after, here again called V1, T1, V2, and T2, for the volumes before and after the change. And this format of the Charles law relationship is usually the one that we invoke and use, okay? So with that stated then, I now have a numerical approach for how I can sort of solve for the second temperature, okay? That's, of course, my unknown variable, my T2. Now my V2 is going to be my 2.5 liters. My initial volume is 9.1 liters. Again, I can really use milliliters, liters in this relationship as long as I'm consistent, okay? I can use pretty much whatever volume unit of measure I want. It just has to be the same on both sides of the equal sign. Now, on the other hand, these T's are temperatures. Now, if I just put 198 here, that would be wrong. I cannot do that, okay? It's really, really important for the gas laws. You pay close attention to what temperature you're using and what temperature you've got. Now, there's given here a Celsius temperature. Whenever I use the gas law relationships, you always want to use Kelvin temperatures. Don't use Fahrenheit, don't use Celsius, only Kelvin, because the Kelvin scale assigns an absolute zero where all molecular motion stops. It's an absolute scale, okay? There's no negative numbers. All right, so the first thing that we got to do if we're going to make this work is we need to figure out what Kelvin temperature we're dealing with here, okay? So what we need to do that is we take our Celsius temperature, which is 198, and we add 273. If I want to be more precise, 273.15, okay? And that gives me my Kelvin temp. Now if I do the math on that, that works out to 471 Kelvin. Okay, that 471 is the number that I need to put in here for my temperature. You must put Kelvin temperatures into these gas laws. I cannot stress that enough. If you don't do that, you're going to get the wrong answer. When we solve for T2, which is our next step, that T2 is going to be in Kelvin as well. Okay, so keep that in mind. So if I do the math here, if I do the division on the left side, I get 0.01932. That's the ratio is equal to 2.5 over my T. Okay, so all I did is just did this division right here, kept the right side the same, right? And then if I multiply everything out, of course, I'll get 0.01932 T by multiplying both sides by T is equal to 2.5, and then T is 2.5 divided by this other number, 0.01932. And if I do the math, I get 129.4. 129.4 degrees Kelvin is my T2. That is the temperature that I need to cool this gas sample to make the volume be constricted from 9.1 at 198 all the way down to 2.5. So I got to cool it a lot, as it turns out. Now, we got a temperature. It's a Kelvin temperature. It's completely valid. But the thing is that they want us to answer this in degrees Celsius. So we're not quite done, okay? We're not quite done because what we need to do is convert back to degrees Celsius from Kelvin. So we got 129.4 Kelvin degrees is equal to my Celsius temperature plus 273. This equation is always going to work for us, okay? So if I want to solve for my Celsius temperature then, I have to take my Kelvin temp 129.4 and then move the 273 over to the other side, so I have to subtract 273 from both sides. That equals my Celsius temperature, and if I do the math, I get negative 143.6 degrees Celsius. Gotta have that negative sign carried along, okay? So again, when you use the gas laws, always use Kelvin temperatures. You can convert into Celsius or even into Fahrenheit if you really want to, after the fact. But when you're doing the math with the equations, you must use Kelvin units. Very important.